Let's look at an inclined plane problem that asks you to solve for acceleration down the inclined plane. These can be particularly challenging if they have friction involved, but let's start with one that doesn't have the force of friction. We're ignoring friction. Let me read you the problem. It says, a 10.2 kilogram box is atop a surface inclined at 25 degrees. The surface is frictionless. Determine the acceleration of the box down the ramp. So I'm going to draw the situation. We've got a ramp here. It's at 25 degrees, and there's a box with a mass of 10.2 kilograms just resting initially, or well, it's sitting on the surface. And so you want to know how much does it accelerate down the ramp. So in terms of processes, when you're looking for acceleration, if you don't have any information like speed or distance or time, you're probably going to need to use forces to solve for acceleration. So the expectation is that you're going to need to use Newton's second law. Acceleration is force net over mass to solve for acceleration. So whenever I have to use Newton's second law, I like to start with a free body diagram, a picture of the forces. And with these kind of problems, it's easier to change your perspective on the problem. So while normally we call this way the y direction, for these problems it's easier to tilt your perspective and call perpendicular to the ramp the y direction and parallel to the ramp the x direction. And the reason why that's easier is this x is going to accelerate down the ramp, so this makes it easier if the x direction is the direction of acceleration. So what that means is if we think about forces, force of gravity is toward the center of the earth. We're expecting the force of gravity. I'm going to draw a free body diagram for this point, but I'm going to draw it over here. I could just blow up this picture. Here's the ramp. Here's the box. Here's I'm drawing my free body diagram. The force of gravity is toward the center of the earth. So what we normally think of as straight down is now, for this new perspective with y this way, it's not completely in the y direction. There's another force that's going on as well. Not only is the whole earth pulling the box down, but the box is in contact with the surface. And surfaces push perpendicular to themselves. So there's going to be a normal force, a force from a surface that's perpendicular to the surface. I'm going to label that F normal, normal force. If there were friction, it might be, let's say, this way, up the ramp, parallel to the ramp. In this case, it says ignore friction. So I only have to write these two forces. And you'll notice that these two forces are not in the same direction as each other. So to solve for the net force, I'm going to need to break one of the forces into components. Specifically, I need to break the force of gravity into components. So if you remember, and if you don't remember how to do this, there's a video that specifically shows you how. If you remember, the way you break the force of gravity into components is to draw in the component perpendicular to the ramp, Fg, in this new y direction, and you draw in the component parallel to the ramp, Fg, in this new x direction, and those are at 90 degrees to each other. This angle here is the same as this angle here. And so you should be able to solve for the force of gravity, the components of them, and for the x component, using this as 25 degrees, and using the force of gravity. Oh, we need to step back. I actually don't know what the hypotenuse is. We have to take one more step. Solving for the force of gravity. mg. 10.2 times 9.8. The overall force of gravity is 100 newtons. So using the hypotenuse of 100 newtons and this angle, you should get the opposite side of the force of gravity in the x direction to be 42.3 newtons. And using the angle and the hypotenuse with the cosine function to get the adjacent side, you should be able to get the force of gravity in the y direction as down 90.6 newtons. And so if I was really doing a good free body diagram, which I love to do a good free body diagram, I'd also show that in this case the force of gravity in the y direction has to be balancing the normal force. So where the normal force is the same value, it's 90.6. Since there's no acceleration, then this way all the forces must balance. And in the y direction the forces balance, but in the x direction I do have one force. So if this is the only force in the x direction, then that actually is my net force in the x direction. It's 42.3 newtons. It's the y component, it's the x component of the force of gravity. Now, if I had friction going up the ramp, I'd have to subtract the two to figure out what the total force in the x direction is. But in this case, I only have this one force as my net force. That's the only force in the x direction, and in the y direction, everything cancels. So this is my net force. I'm one step away from finding the acceleration. Acceleration is net force over mass. Net force in the x direction is 42.3. Mass is 10.2. So the acceleration of this block down this ramp is 4.14 meters per second. And that's how you take a look at solving for these problems on inclined planes.